So welcome again. We're gonna continue with our example as we said. That we're gonna continue with our example. Then let us proceed with the example as we said. So we can see that now the second example. Second example is fn defined from minus pi to pi by the following formula to the real number. Fn of x is given by n cosine of nx. So now our problem is, the question is, can we use the Bepo-Levi theorem, or the monotone convergence theorem? This is the question. So we must check. To answer this question, we must check the hypothesis of the Bepo-Levi convergence theorem. So what the first hypothesis is to check if the function fn is positive. We must check if fn is positive, right? Is fn always positive? Let's compute fn, for example, so fn of x is defined generally as cosine of nx. So take x, it will be positive if we can compute this and always find a positive number if we compute this. But take this x, that is equal to pi over n. And you can see that this is an element of minus pi to pi, so it is an element of the domain of fn. So if fn were to be positive, if we compute, we must find a positive number. So let's see if this will give us a positive number. This will give us cosine of n x stars, which is n cosine of n times pi over n, which is equal to n cosine of pi, which is minus 1 times n, which is less than 0. So this is not possible, right? So this is not possible. We cannot use fn is not positive. So we cannot use a Bepo-Levi theorem. But what can we do then? We can only compare if the limit of the integral and the integral of the limit is the limit of the integral and the integral of the limit are the same. So that's the only thing I can do. So let us see if what will we give. If we compute, for example, the integral from minus pi to pi of fn of x dx, it will give us n, the integral from minus pi to pi of cosine of nx dx, which will give what? Which will give us, if we compute, we can see that this is so sine of nx from minus pi to pi. So if we compute, we will see that it will give us 0. It will give 0. So the limit of the integral, the limit of the integrals of fn dx is 0. But then, can we compute the limit of fn and compute the integral and see what we will get? So let us now try to compute the limit as n goes to plus infinity of fn, and see if we'll get something. This is the limit as n goes to plus infinity of n times cosine of nx. But this sequence doesn't have any limit. This limit doesn't exist. Why? Because if we consider x to be equal to pi, so this will give us n times minus 1 to the power n, but we have two subsequences of this sequence that converges to different things. For example, 2n minus 1 to the power 2n converges to diverges to plus infinity, but 2n minus 1 times 2n minus 1 the radius to minus infinity. So this sequence doesn't have any limit. And then, so this sequence doesn't have limit for any value of n. So we cannot make sure that this limit exists. And then it doesn't make sense to permit to interchange the integral and the limit here. Here we cannot interchange the limit and the integral because the limit of fn doesn't exist. Let's take a third example. The third example is fn of x is equal to n modulus of cosine of nx. So we define it from the interval minus pi to pi in the real number. So we have to see, can we use the Bepo-Levi theorem? The same question. This is the same question that we're gonna solve now. Let's see what we can do for this question. First of all, we must check if the sequence is a positive, but we can already see that n is positive multiplied by cosine, the absolute value of cosine of something, it is positive. So we have positive numbers for any x in the interval minus pi to pi. So our sequence is a sequence of positive numbers. So now we have to see if the sequence is monotone, so it is increasing. So we must check if we have this fn less or equal to fn plus 1. That is equivalent to say that for nx in minus pi to pi, we must have fn of x less or equal to fn plus 1 of x. So we must check this, if this is possible, if this is true. We must check if this is true. So then, is this relation true for any x? Let's see. Take, for example, x equal to x stars equals to pi over n plus 1. This is an element of minus pi to pi. And we can see that fn of x stars, which is equal to n plus 1, fn plus 1, sorry, which is equal to n plus 1 cosine of n plus 1 times pi over, oh no, let's take 2 here, pi over 2 times n plus 1. We can cancel this. This is 0. But if we consider the other one, the other term, it will not be 0. The other term, sorry, here, consider the other term, fn, and see if we will get something that is less than this. Consider the other term, but fn of x stars, which is n, modulus of cosine of n times pi over n plus 2 plus 1, which is n times cosine absolute value of n over 2 over n plus 1 multiplied by pi over 2. But this is not equal to 0, then it is strictly greater than 0. So we don't have this. So we don't have this. This is not true. This is not true. Then we are not sure. We didn't make sure that the sequence is an increasing sequence. Then we can also say that we cannot apply it directly, but we could also check if the sequence was instead decreasing. That means that we had this, because if the sequence is decreasing, and we have also that the integral of the first term of the sequence is not finite, is not infinite, then we can still interchange the limit and the integral. but be good about that. In our case, f1 is cosine is a continuous function on a bounded interval, so the interval is always bounded, so it's always finite. Therefore, if we had that our sequence was decreasing, we can also use this, but this sequence decreasing, take again x stars to be equal to pi over 2n. We can see that with fn of x stars, it will be 0, while fn plus 1 of x stars will be strictly greater than 0. So the sequence is not, is one more time, not decreasing, so we cannot apply. So the only thing we can do as previously, we can try to compute the integral from minus pi to pi of n cosine of nx in absolute value dx, which is what? Which is the integral from minus pi over n and pi over n of what? Of cosine of t dt. So we assume that pi is slightly greater than 2. So we assume that n is slightly greater than 2. So we have something like that. We have something like this. We are here minus pi over 2 is there, and pi over 2 is here. So pi over n will be minus pi over n will be somewhere here, and pi over n will be somewhere here. So we know that cosine here it is 0, and it will go to 1. So we don't care about this. So we have something like that. So the function is always positive and symmetric. So what we're gonna do is, this is 2 times the integral from 0 to pi over n of cosine of t dt. So this is what? This is 2 times sine of pi over n minus sine of 0, which is 0. So this is 2 sine of pi over n. So if we compute the limit as n goes to plus infinity of the integral from minus pi to pi of n modulus of cosine of nx dx, it will be the limit as n goes to plus infinity of 2 sine of pi over n, sine of pi over n, which is 0. Then let us see if we compute then the limit as n goes to plus infinity of n cosine of nx modulus of nx, this is plus infinity. This limit is plus infinity because this is always positive and bounded, so this is going to plus infinity, so this will be plus infinity. And then if you want the limit of the integral of the limit from minus pi to pi as n goes to plus infinity of n modulus of cosine of nx, this will give us plus infinity. You see that the limit that we get with the integral that we get with the limit inside is different from the integral that we have with the limit outside of the integral. So we cannot say that the limit, so we have seen that the limit of the integral is different from the limit of the integral of the limit. So that we could also think that something like that can happen because we have seen that the Bepo-Levi theorem was not fulfilled. So